Hi, this is Descriptive Statistics Part 1, covering 1.3 and sections 1 through 4 from Chapter 2. This is more typical of what a video lecture will be like. There are notes posted on Foxtail you can print to follow along with. Basically, we'll cover some concepts, we will do some examples, and there will be boxed instructions on how to do different things. So let's just get going. We're going to start by reviewing what descriptive statistics are. So descriptive statistics are, hopefully you're thinking about what that is. They are numeric or graphical summaries of data. So we're assuming that we have taken a sample from a population and we have lists of raw data. That raw data can be in the form of qualitative or quantitative data, either one. But either way, we need to be able to summarize it to be able to use it. So first we're going to look at some graphical descriptive statistics. First thing is what we call a frequency table. Frequency table can be used to summarize either qualitative data, all right, things that get put into categories, or quantitative data. And quantitative data, remember, breaks into discrete or continuous, and we can use frequency tables for both of those. Okay, and we'll look at examples of all of those over the course of this particular video. Okay, we're going to create a frequency table using this set of data, the number of letters in the last names of Math 240 students. I have the data values listed there. So let's just name what kind of data we've got here. Its number is, so it is obviously quantitative, and out of quantitative, numbers of last names has to take on particular values. So this would be discrete data. Okay. All right, let's expand this so we can write in those little boxes. Okay, 4 columns in a frequency table. First column is the variable, in this case, number of letters. Now, each row we want to make correspond to just part of the data. We don't necessarily want to list out all of the values that we have in the list, which is 2 to 12. We want to kind of group values together. So if we take and put 2 and 3 together, and then 4 and 5, 6, 7, 8, 9, 10, 11, 12, 13. Next column is frequency, where we're just going to count up the number of data values that fall in that range of values. So if we look at 2 to 3, there is 1 value. So that happens one time, so we put a 1 in the frequency column. 4 and 5, we've got 1, 2, 3, 4, 5 times. Frequency of 5. 6 to 7, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8 to 9, we've got 1, 2, 3. 10 and 11, there are 0. And 12 to 13, there's 1. So that last column that last row, we can make a total row. If we add up the frequency column, we should end up with the same number of values that we have in our data set, which we do. We got 20. Relative frequency is going to be the proportion of the frequency to the total number. So for 2 to 3, we've got 1 over 20. That's the fraction form. We can also give relative frequency in decimal or percentage. So we'll put this in decimal form as well. So that's 0.05. For 4 to 5, our relative frequency is 5 over 20. In decimal form, that's 0.25. 6 to 7, we have 10 over 20. so that's 0.50. 8 to 9, we have 3 over 20, so that's 0.15. And then 10 to 11, we have 0 over 20, so that's just relative frequency of 0. 12 to 13, we have 1 over 20, so again, that's 0.05. All right, so think about what that column should add up to. Well, we've included all of them. We should get to 100%, which in this case we do. So if we add up those decimals, we get 1.00, or 100%. Now, those relative frequencies in decimal form, we didn't have to round. They turned out really as nice terminating decimals. So when we add them, we are sure to get 1. That doesn't always happen, and we'll look at an example later. Cumulative frequency is kind of what it sounds like. We are going to accumulate frequencies as we move through the rows. So we look at 2 to 3. We so far have accumulated 0.05 of the data. Then as we move to 4 to 5, we now have the 0.05, that 0.25. So that becomes a total of 0.30. And then we move to 6 to 7. We accumulated the 0.3, and we're going to add to that the 0.5, so we get 0.80. And then for 8 to 9, we add 0.15, we get 0.95. For 10 to 11, we don't add anything, so that just stays at 0.95 again. And then for 12 to 13, we add 0.05, and that gets us up to the total frequency of 1, which it should. Okay, so that gives us an example of a frequency table. Here I've got some definitions of those columns, reminders of how to calculate them, and the forms that they can take. All right, let's move on to the next thing, which now we're going to start to look at some graphs. First one is a bar chart. And let's take a look at the 2 examples and ask ourselves what kind of data is being described in these. And if we look at the columns or the bars, depending on which one, all right, we see we've got words describing for both of those. So what we've got here is qualitative data. So bar charts, they describe qualitative data, so things that can't be measured in numbers. And bar charts consist of bars or rectangles with, you notice they have space or gaps in between them. And the heights, as in the first one, or the widths, as in the second one, they're either going to be the frequency, or they can also be the relative frequency. Now, both of these examples are frequency, right, which we can tell because the heights and the widths are measured in integers. So those are frequencies. A lot of times relative frequency can be more useful. When you have a bar chart and all of your columns are labeled, it's fine to use frequency, but if you isolate one particular value, one particular category, if you use a relative frequency, that's all you need because it's a percentage or it's a proportion. If you give a frequency, then you also have to give the total number that it's out of. All right, other things about bar charts. The bars can be, as we see in the examples, they can be vertical, like the first one, or horizontal like the second one. And we base the frequencies off of a frequency table. So let's look at another example here. We're taking some more data and going to want to create a frequency table and then also a bar chart for this qualitative data, which is the the years of online math 240 students. Now I'm going to make one little change here. We're actually not going to do cumulative frequency. Doesn't make as much sense when we have qualitative data. Okay. Filling in the frequency table for freshmen, frequency is 0. No freshmen taking online math 240. Sophomores, we count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Juniors, 1, 2, 3, 4, 5. Now, to get the seniors, we know that we have a total of 20. So far, sophomores and juniors gets us up to 15, so there must be 5 seniors. Or we can go through and count. 1, 2, 3, 4. And you know what? There is one more senior here that got left off the list. Sorry about that. So get us up to 20. Okay, we can create relative frequencies, and for freshmen, it's 0. So let's use percentage this time, so that's 0%. Sophomores, 10 out of 20, that's going to be 50%. And juniors, 5 out of 20, that's 25%. And for seniors, 5 out of 20, also 25%. And that adds up to a nice 100%. Okay, to create the bar chart, along the horizontal, let's put the categories. So freshman, sophomore, junior, senior. Put the, let's do relative frequencies. So 50%. And we need 25%. So for freshmen, we're not going to draw a bar at all. For sophomores, we'll draw a bar up to that 50%. For juniors, we'll draw a bar up to 25%. Here, I'm going to redo that. It's a little bit tall. Okay, so there is the bar chart for years of students in online math 240. All right, here is a box that gives how to create a bar chart. All right, so basically goes over all the things that we just did. It's a good reference for how to do a bar chart to look at later. All right, let's look at the next type of descriptive statistic. Again, this is a graphical descriptive statistic. It's called a histogram. And just like bar charts were for qualitative data, histograms are for quantitative data. And if we look at the two examples, let's look at the second one, cappuccinos made per hour. Okay, well, cappuccino that's a number of cappuccinos is going to be a discrete piece of data or variable, all right, because we're going to count those number of cappuccinos. But if we look at the other one, it's the speed of light. We measure speed, we answer the question how much. So that is measuring a continuous piece of data. All right, the other thing that we want to look at the difference between these and the bar charts are that, well, here, let's go through what is being asked here. Bar chart 4, like we have said, it's quantitative data. And the bars are always vertical with no space in between, all right, or no gaps. All right, we start with the frequency table just like we do for the bar chart, but we don't have always sort of discrete things to use to create the frequency table. So or I should say, we don't have the categories to create the frequency table or to create the labels on the graph. So we use classes instead of categories. So those classes are intervals of numbers. If we look at our two examples, there's a couple ways that we can label those. For the discrete example, we just labeled each of those bars with the range or the interval of values. So the red one is going from 0 to 3, the blue one 4 to 7. So in that case, we have just the classes are labeled. And in the first one, it's not the classes that are labeled, but it's the boundaries in between. So we've got class boundaries are labeled. All right, to create a frequency distribution table for quantitative data, we have to break the range of data values into class intervals. Now, we already did that for that first frequency table that we did. So we're going to do this again. It's going to add a couple elements to it. And we want to create the interval such that each of the values is contained in just one class interval. So we're going to use this set of exam score data. Okay, and we're going to use class boundaries of 30, 40, 50, 60, 70, 80, 90, and we're actually going to need to put in 100 and 110 as well. Go back and fix that. Oops. Seems like test scores. Let's see, I don't have it written there. Okay, good. So for these boundaries, we're going to have to assume that it is less than the upper boundary. Okay, so if we have a class interval that goes from 30 to 40, we're going to assume that values included in that interval are going to be equal to 30 up to, but less than 40. Okay, in 40 to 50, equal to 40 up to less than 50. Okay, so let's find the frequencies for this set of data. So 30 to 40, we have got one value. And 40 to 50, all right, there's one value. All right, to 50 to 60, if you note those up, there are two values. 60 to 70, there's four values. And 70 to 80, there are seven values. 80 to 90, there are five values. 90 to 100, there are two values. And there's one value right at 100. So in that 100 plus category, we've got a 1. Okay, so we'll see. One thing I want to comment on is the total here is 23. I think on the notes it says 24. In fact, all right, so there's 24 or 23 test values, test score values. Okay, now the relative frequency, here's a case where this isn't gonna, we're gonna have to do some rounding here. So let's establish that we're gonna go to 2 decimal places. All right, so we calculate it the same way. All right, we're going to take that frequency over the total. All right, so we're going to have 1 over 23. All right, and that gives us 0.04347, etc. So if we round that, that's going to round to 0.04. All right, so frequency for the next interval is also 1, so that's going to also give us a relative frequency of 0.04. All right, if we take 2 divided by 23, we get 0.086956, etc. That one's going to round to 0.09. All right, for the next class interval, 60 to 70, we've got 4 divided by 23. All right, that gives us 0.1739, ... so that'll be 0.17. And then 70 to 80, we got 7 divided by 23, and that's 0.3043, so that's going to round to 0.3. And then we've got 5 divided by 23, so that's 0.21739, so that'll be a 2, 2, and then we have a frequency of 2. That relative frequency we know from above is 0.09, and then another frequency of 1, which we know is 0.04. Okay, we had to do rounding. So when we add this relative frequency column, we know in theory it should equal 1, but because we're rounding, we are likely to get, something that's not quite 1. So if you add these up, you're actually going to get 0.99, okay, which is approximately 1. And we know because we rounded that that's the case. Let's use those relative frequencies to create a histogram. All right, so let's recenter on that. So we're going to break that horizontal into those class intervals. So 30, 40, 50, 60, 70, 80, 90, 100, 110. All right, and we'll go ahead and label them. Now, we're doing these manually. Usually, if you're going to do a histogram, it's going to be something a piece of software or Excel is going to do for you. Doing it manually a couple times, make sure that we know exactly how they work and what the pieces are. You can do yours as precise as you want. Mine, just given the format that I'm using, it's not super easy to make it super precise. So to do the relative frequency, I'm just going to take the relative frequency that we have and label those ones. The highest one is 0.3, and then we've got a 0.17, which is going to be about right there, and then a 0.09, and a 0.04, and then the last one that we need on here is 0.22. All right, so 30 to 40, we're going to put a bar over 30 to 40 that goes up to that 0.04, and then same for 40 to 50. For 50 to 60, we go up to 0.09, and 60 to 70, we go up to 0.17. 70 to 80, that's where we're going to go up to 0.3. 80 to 90, we go to 0.22. 90 to 100, we go to 0.9. And for 100 to 110, we get 0.04. All right, so that gives us the histogram for our exam score data. All right, we've got the box telling us how to create a histogram, gives us each of those pieces. Let's look at this next thing. We've got 3 histograms. The first one on the far left, we're assuming we have a small data set. We can see those bars on those histograms really distinctly. As the data set gets larger, the one in the middle, all right, it becomes a little less distinct. And then as we get a really large data set on the far right, we can see that there is a distinct curve, all right? And when we talk about histograms, we typically just think of that. We just think of that curve piece, not necessarily think of the rectangles underneath. So we're just kind of looking at this piece. All right, we do a lot of curves that look like that, right? We got the vertical and the horizontal. Okay, we're going to move on to another section. Good time to take a break if you want. The next section, we're going to move on to numeric descriptive statistics. First type are quartiles and percentiles, and we call those measures of location of data because they look at a particular data value and they compare it to the other data values in the data set. So we're going to start by looking at these 23 test scores. So that should say 23, not 24. All right, so we have them listed there. Percentiles and quartiles answer questions like these ones. What exam score has 75% of the values less than it? Or what percentage of values are less than a score of 72? If we want to define, start to define what we mean by those, percentiles divide ordered data into hundredths. All right, which that's probably not very surprising. And quartiles divide ordered data into quartiles. Again, the word kind of says what it is. We're going to start off by finding a percentile value. Now, this description of how to do it is more complicated than what it will be in actually doing it. So, if we want to find a percentile value, you'll find that there's a lot of different ways described as to how to do it. The one that we are looking at here is the same as in the textbook, so you'll find consistency there. So first, just identifying just some different variables. N is the total number of data values. K is as in the kth percentile. So for example, if we have the 75th percentile, or little abbreviation here, that means that N is equal to 75. I is just an index. It's the ranking of a data value in an ordered list. All right, so here is where we look at the steps. First, we order the data from smallest to largest, then we calculate the index. All right, we just take whatever K is, put it over 100, and multiply that by N plus 1. And then it depends on whether I is an integer or not. If it's an integer, then we just take that data value, the ith data value in that ordered list, and that's the kth percentile. If it's not an integer, we round I down and up, and then we take those two indexes and we average them together, and that's the kth percentile. So let's follow that to find the 75th percentile of our exam scores. So first of all, we're going to order the exam scores from smallest to largest. So there's the data list ordered smallest to largest. All right, N is 23. We're wanting the 75th percentile, just to remind us. So K is 75. And here's where we need to do some calculation for I. We take K, which is 75, over 100, and multiply it by N plus 1, so that's going to be 24. All right, that actually gives us a nice round integer of 18. So that is that's our index. So we want to count up to the 18th value in this ordered list, and that's going to be our 75th percentile. Now, 18 is closer to 23, so I'm actually going to count backwards. So we have 23, 22, 21, 20, 19, and 18. So 82 is the 18th value in the list. So that means that 82 is the 75th percentile. All right, we got to remind ourselves what that means. So if it is the 75th percentile, that means that 75% of the data values, or in this case, it's exam scores, are less than that value of 82. All right, so if your score was 82, that means that 75% of the other exam scores were less than yours. All right, let's now look at another example. Let's use the 90th percentile. This would be a good chance to pause, work this out on your own, and then come back and see how it's done. Check your work. Okay, so we want to identify the N, which is still 23, K, which is now 90, And we want to calculate what that that index is. So we're going to take 90 over 100 times, again, 24. This time we don't get a nice integer, we get 21.6. All right, so that means we want to go to our list and we want to identify the 21st value and the 22nd value and take an average of those. Okay, so I'm just going to say the 21st value all right there, the 22nd all right there. So, you know, going from the top of the list, we got 23, 22, so the 22nd is 97, and then 21 is 91. All right, so what it says to do is we average those two. So 91 plus 97 divided by 2. All right, we get the 90th percentile is 94. Okay, so 94 is the 90th percentile. All right, then you're going to be able to interpret what that means. All right, that means that 90% of the scores are less than 94. Okay. Another question we can ask ourselves using this idea of percentiles is what percentage of values are less than a score of 70? And the answer to that is what we call the percentile rank. So we're going the other direction. So we're starting with a value from the list, and then we're asking what its percentile rank is. So here's how we do that. So again, you know, this is going to sound more complicated than actually doing it. First, we order the data smallest to largest. Then we identify this value x, which is the number of data values, counting from the lowest value up to but not including the data value that you want to find the percentile rank. And then part 3 is identify this value of y, which is the number of data values equal to the data value that we're interested in. Again, n is the total number of data. And then we calculate this thing, x plus 0.5y over n times 100. Round it to the nearest integer, and that gives us the percentile rank. Okay, so let's look at this value of 72. What is the percentile rank of an exam score of 72? Okay, so we want to find x, which is the number of values that are less than 72. So referring to your list of data values, that is 8. And then y is going to be the number of times 72 shows up in the list, basically. And that's just one time. N is 23. Okay, so if we take x plus 0.5 times 1, divide it by n, which is 23, and then multiply that by 100. Okay, so that's like 8.5 divided by 23. And we get a value of 36.95, not terminating, but we can round that up to 37. So that is telling us 72, the exam score 72 is the 37th percentile. Let's look at another example. Let's look at the percentile rate for exam score of 74. So we want our value x, which is the number of values less than 74 in our list, and we get that value to be 9. And then y is the number of times 74 shows up in the list, and it shows up 3 times. So to get that percentile rank, then we're going to take 9 plus 0.5 times 3 over n, which is 23, and then multiply that by 100. So we get 10.5 divided by 23 times 100, which is equal to 45.65. And dot, dot, dot. We want to round that to, we want to round that up to 46. So that tells us that 74 is the 46th percentile. Percentiles work best when we have a really large data set, so that's why we see a big jump from the previous one we just did, which was just one less than one, further, down the list from this one. We jumped from 37 to 46 percentile. If we had a lot bigger data set, we wouldn't see that big of a jump going from one to the other. Okay, let's look at quartiles now. There's 3 quartiles, all right, because we said the quartiles divide the data into quarters. All right, so different textbooks use different labeling. I thought I'd gotten through and fixed all that. We actually want to label the first quartile as Q with a subscript of 1 for first quartile. If we relate it to a percentile, it's the 25th percentile. The second quartile, it's labeled M. That's actually correct. It's labeled N because it's also the median. We'll talk about median later when we talk about measures of center. The median is the 50th percentile, which means it's the middle value, 50% or below, 50% or above. The third quartile, which we're going to use uppercase Q with a subscript of 3 to stand for, is the 75th percentile. Okay, so quartiles divide the data into 4 quarters. About 25% of the data values are in each of the quarters. All right, so if we label this, we got Q1 right here, and the median in Q3. So 25% of the data values are in each of those quarters. Each quarter has roughly the same number of values. You might have a data set that is not divisible by 4, so you're not going to end up with the same number of values, but they're roughly the same. Okay, and then it talks about the median again. We're going to find quartiles a little bit differently than we find percentiles. We could use that same method, but there's actually a method that works just a little bit quicker without the fussy equations. So finding quartiles, we arrange the sample data values from smallest to largest, and then we first find the median. Okay, if we have an odd sample size, then M, the median, is just the middle value. If the sample size is even, though, there isn't a middle value, so we take the 2 middle values and we take an average. All right, then we repeat that for the lower half of the data to find the first quartile. And so in other words, the first quartile is the median of the lower half of the data, and the third quartile is the median of the upper half of the data. All right, so let's go through an example. And here's our exam scores. They're listed from smallest to largest. All right, we've got sample size is 23, so we have an odd number. So we want to find the middle data value in our list. Middle data value is the one that's going to have 11 less than it and 11 greater than it. So, all right, if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, here is our median value, because then it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 greater than it. Okay, so that the median breaks the data into the lower half, and we're not going to include the median in that lower half or the upper half. So breaks it into two sets, the lower half and the upper half. So we'll call them that. So to find the first quartile, we're going to find the median of this lower half. All right, so the lower half has 11 values. So again, we're going to be able to find a middle value. All right, it's going to be the sixth value from the bottom, right? So there's 5 in each half. 1, 2, 3, 4, 5. All right, 1, 2, 3, 4, 5. So there's our first quartile. And then the same thing for the upper half. 1, 2, 3, 4, 5, 6. There's our third quartile. All right, so you can see that 82 has 1, 2, 3, 4, 5 values greater than it, 1, 2, 3, 4, 5 values less than it in the upper half. So it makes it the median of the upper half. All right, so we've got our 3 quartiles. Our Q1 is 63, and our median is 74, and our third quartile is 82. Okay, another thing that we can look at here is we can think about the spread in each of these quartiles. So by spread, we mean the difference between the largest value and the smallest value. So spread. So for the first quarter, we go from 63 down to 34. All right, so that makes a spread of 18. The second quarter, okay, all right, going from the first quartile to the median, we have 74 minus 65. So that's a spread of 9. The third quarter, going from the median to the third quartile, we have 82 minus 77. So 82 minus 77, we get a spread of 5. And then the fourth quarter of data, we go from 100 to 85. So we get 15. Okay, so one thing that we can ask ourselves is, where's the data concentrated? So remember that there is roughly the same number of data values in each of these quarters of data. So if we look at the first quarter, 34 up to the first quartile, we have 6 values. The first quartile up to the median, we have 6 values. Median up to the third quartile, we have 6 values. And then again, because we don't have something divisible by 4, this last quartile only has 5 values. Okay, so each quarter has the same number of values. So if we look then at the spread, we can sort of talk about data concentration or how spread out data is. So that first quartile, oh, you probably already noticed this. That should be 28, not 18. There we go, much bigger spread. Okay, so the spread is 28, but there's only 6 values. Okay, so that means that we could say this is the most spread out of the quarters, or it has the most spread. And then we look at the third quarter, the spread is 5, all right? But it has the same number of data values in it. So it's the most concentrated or the least spread out. So I kind of like to put it in the concentration form. So most concentrated. Okay, we'll come back to this idea of spread and concentrated and kind of what it means in some of our other examples. All right, but let's move on to look at applications of quartiles. So we've got a couple. One is to determine if we have outliers in our data, and the other one is to create a box plot. A box plot would be another graphical descriptive statistic. So to determine if data set has outliers, we have a process using the quartiles, but let's define what we mean by an outlier. An outlier is a value in a data set that's either unusually large or small relative to the other values in the data set. Okay, so it might seem like it doesn't belong, all right, but we have a way to measure whether it's an outlier or not. So that's the first thing we want to do. So here is how we do it. We take the difference between the upper and lower quartile, or actually in the terminology we're using, the third and the first quartile. And this is called the interquartile range, or the IQR, Q sub 3 minus Q sub 1. All right, then we look at the lower bound. Sorry about that. And we take the first quartile and we subtract 1.5 times that IQR. Any values less than that are outliers. And then we look at the upper bound. And we take the third quartile and add to it 1.5 times the IQR. Any values greater than that are outliers. Okay, so let's look at an example. A middle school is applying for a grant to add fitness equipment to its gym. The principal surveys 15 students and asks how many minutes a day the students spend in the gym. Okay, so let's apply this method to see outliers. Here are the list of minutes exercising by the 15 students interviewed. We want to find the quartiles, determine if they're outliers. Okay, first thing we need to do, hopefully you're noticing that list is not ordered, so we're going to have to order the list. Okay, there is our ordered list. And remember, our sample size is 15. It's an odd number. So we're going to have a middle value. So our middle value is going to be the 8th value with 7 on either side. So 1, 2, 3, 4, 5, 6, 7. There's our middle value, our median, just to make sure we got 1, 2, 3, 4, 5, 6, 7 on either side. So we can think of this as our lower half and our upper half of data. So we want to find the middle value of each of those. So again, we've got an odd number on either side. So 1, 2, 3, 20 is our first quartile. So we have 3 on either side of that. And 60 is our third quartile. And we have 3 values on either side of their third quartile. Okay, let's calculate first the IQR. That's that interquartile range, which is the third quartile, 60 minus the first quartile of 20, so that's 40. Okay, we want to look at the lower and upper bounds for outliers. So the lower bound, we take the first quartile of 20. We're going to subtract 1.5 times that interquartile range. All right, we get a negative value. We get negative 40. All right, there's not possible for it to be a negative number, so no outliers, no that are a lot less than most of the data values. So let's look at the upper bound for outliers. 60, which is the third quartile, plus 1.5 times 40. Okay, that value is 120. All right, there is one value, 300, that's greater than that upper bound. So it is an outlier. And that's because it is greater than this 120 that we found. Now we also have the value 120. So that could go either way. Typically the rule is if it's just greater than that value. So equal to is fine. So question now is, what do we do with an outlier? Do we just throw it out? Do we include it? And it depends on why it's an outlier. So there's three possible reasons we can get an outlier. It could be that the value is observed or recorded incorrectly, and so there was some kind of human error. Second one is that it was, recorded correctly, but it came from the wrong population. Like it came from something that we weren't intending to sample. And then the third possibility is that the value is completely correct, but it just represents a very unlikely event, something that has a really small probability of occurring. So in the first two cases, the first case, we either want to fix, and if we can't, we have to throw it out or delete it. And in the second case, we need to delete it because it's not right from the right population. And in the third case, we may want to proceed with the data value, but then we may want to also try to do the analysis without the data value and see what the difference is. But we can't just throw it out. We kind of have to include it because it is a valid data value. So let's think about how these can happen, or how these three things could have happened for this example. So, given we're measuring minutes of exercise by middle schoolers, so what's something that could have happened such that the value is observed or recorded incorrectly? So for that one, it could be that someone wrote 300 instead of 30, right? They just put another extra zero on there. So you got to look back and kind of question that number. If you can determine that it was supposed to be 30 instead of 300, then you got to, use the 30 and then recalculate. Okay, now what about the different population? Well, what if someone gave minutes of sleep instead of exercise? All right, that's one way you could have gotten 300 instead of 30. All right, or the value is correct but represents a really rare, very small probability event. And in this case, I would say that yes, that would be very, very small probability. Someone probably has, maybe exercising a little bit too much for their age or their situation. Okay, let's look at the second application of quartiles. That's box plots. And it's a graph that's based on 5 values. And sometimes these 5 values are called the 5-point summary. It's the minimum, maximum, first and third quartile, and the median. Okay, let's go through the process again, find median, quartiles, and outliers, and then we're going to use that to find a box plot. So here we've got number of shoes owned by 18 individuals, and I've also got the ordered list here for us. So first thing, to find the median, because it's 18 individuals, it's an even number. We're going to find the mean of the middle two numbers. Okay, so 18, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So the median, right, is right here in between these two 15s. So we take the average of 15 and 15. So that gives us 15. So our lower half of the data, is the 3 to the first 15, and the upper half is the second 15 up through 37. And then we find the median of each of those. So there's 9 in each of those, so we're going to have a middle value. So 1, 2, 3, 4, 5, that's the first quartile. That's 12. And 1, 2, 3, 4, 5, third quartile is 23. So let's figure out if we have outliers. The interquartile range, 23 minus 12, okay, we get 11. So the lower bound for outliers is we take the 12 minus 1.5 times 11. We get a negative 1.5, so no outliers that are a lot less than the other values. And then the upper bound, 23 plus 1.5 times 11 gives us a upper bound of 39.5, which there are no values that are greater than that, so we have no outliers. All right, no outlier number of shoes owned. Okay, so now we got to use that information to create a box plot. Okay, the box plot consists of a box and what we call tails or whiskers. So we start by drawing the box, which is, we can think of as a rectangle. So rectangle. Okay, the sides are the quartiles. So the left side would be the first quartile. So in our case, our first quartile is 12. And the right side is our third quartile of 23. Now, in between those, we have the median. So to show the median, we do a vertical line. And we want to place it, relative to the 12 and the 13. So it's 3 above the 12, and it's 8 below the 23. So, and we also draw it as a dotted line to show that it's different than the quartiles. All right, so that's the box plot. And we draw the box, we draw the vertical dotted line for the median, and then we want to label those things too. Okay, the tails are lines drawn from either side of the box down to the minimum value that's not an outlier and the maximum, and to the right to the maximum value that's not an outlier. Since we don't have any outliers, the tails are just going to go to the minimum value on the left and the maximum value on the right. So our minimum value is 3. All right, so we want this to be, in proportion. So 3 to 12 is 9. We got 15 to 23 is 8. So we want it to be a little bit longer than that span. So we can go like that. And then we can label that. And then we want to go from 23, a tail from 23 to 37. All right, so that's 14. And I probably barely gave myself enough room here. Okay, so 37. All right, so that is a box plot. Okay, and it has the 5-point summary, right? It's got the min value. It's got the first quartile. It's got the median. It's got the third quartile, and it's got the max value. Okay, now we're going to do another example that has outliers, and we'll show how to do that. But let's look at how we interpret the box plot and what it can tell us. The box plot gives us a good visual to identify that idea of spread and concentration. All right, when we've got a longer tail to one side, that usually means that the data is skewed that direction. Okay, or it's spread out further in that direction. And So we can look and we can see that the fourth quarter of the data from Q3 to the max, all right, we got the most spread. Okay, because remember, there's the same number of data values between 23 and 37 as there is in between in the other quarters of the data. And which one is the most concentrated? All right, well, the most concentrated is the second quarter. All right, that's the most concentrated. It has the same number of values as the other quarters, but its spread is only 3. Okay, all right. We'll do one more example. Before we go on to another example, let's actually look a little more closely at this box plot. We talked about this before when we just had the quartiles and the median, but now we have the box plot, so maybe we can kind of put these together to visualize. So the spread of the first quarter, okay, so what we're doing is we're taking the difference between the first quartile and the min. Okay, so if we take that difference, we get 12 minus 3, we get 9. For the second quarter, okay, we get the difference between the median and the first quartile. So 15 times minus 12, we get 3. And the third quarter of the data is what goes from the third quartile to the median. So that's going to be 23 minus 15, so that's 8. And then the fourth quarter of the data, we're going to go from the max to the, or go from the third quartile to the max. So we take that difference and that's going to give us 14. Okay, so that's the spread of each quarter. Each of those quarters has the same number of data values. So which quarter has the most spread or is the least concentrated? Okay, so that's going to be the one with the largest spread number. So that is quarter 4 because it's 14, larger than the others. Which quarter has the least spread or is the most concentrated? Okay, well, the second quarter, the spread is only 3. Okay, now if you compare that to the box plot too, that's easy to see because the tail on the right, that's the longest part, and that distance in the box, in the rectangle, from the left side to the median is the shortest spot. Okay, so that also is that identified. Okay, we did not have any outliers, so we can skip this question number 4, but let's look at another example and create a box plot. Unfortunately, this got split up. Okay, so here's our minutes exercising data. So just a little reminder of the values here. The minimum was 0. The first quartile is 20. The median is 40. The third quartile is 60. And we had an outlier of 300. And the other thing we need is the max value, which was also 300. Okay, so let's use those values to create the box plot. I'm going to draw the box to start off with and label the left side with the first quartile, which is 20, or the right side with the third quartile, which is 60, and then the median is 40, which is right in the middle. Here, I can get that more in the middle. Okay. The tail on the left is going to go to the lowest, the minimum value, and so that's 0. So put the tail out there, I'll label that. Now to the right we have an outlier, and the outlier is at 300. Now I don't, even though I set myself up way over here on the left, because it's so large, I'm not really going to have space to put this on here. So this is going to be kind of condensed. Now, the tail is going to go to the largest value that's not an outlier. So that's the 120. Okay, so that 120 would need to go probably even farther than that. All right, now to show that outlier, which needs to be even farther to the right, but I've run out of space, we're going to not include it on the tail, but just make some kind of mark to show where it would be. Okay, now because we haven't been able to write the box plot exactly right, we just have to keep that in mind, that this distance between 60 and 120 really is farther than that, and the distance between 120 and 300 is farther than that. Okay, let's answer these questions. Concentration of data. Which quarter has the, let's start with most concentrated data. Okay, so here we're starting with a box plot, and we want to determine what these values are. Okay, notice that there is no tail to the left. So let's see if we can figure these things out. Minimum value. Well, there's no tail to the left, but the box plot starts at 1. So that means the minimum value is 1. Maximum value, we go to where the tail goes to the right, it goes to 7. So we got maximum value of 7. Okay, first quartile. It's always where the box starts on the left. So that's at 1. Okay, median, there's no dotted line. So let's come back to that. Let's look at third quartile. Third quartile is 5. That's where the right side of the box is. Okay, now let's think about that median. Let's put it over here. Since we can't see it, it's not showing up. That means it's either the same as the first quartile, 1, or it's the same as the third quartile, 5. We can't tell from the picture that's given. Okay, that's all for Descriptive Statistics Part 1. Please respond if you have questions. Give the assignments a try. Till next time. Bye-bye.